Hello, my name is Omar Rana. I work as a professor in computer science at Cardiff University, and I would like to give you a talk on large-scale science. So thank you to BNU for inviting me to give this presentation. You have my email if you would like to ask further questions. So just to give you context for this, so science today is a team sport. So you can see some examples of covers of a important science magazine here. So many examples here demonstrate the importance of working together for scientists across the world. So whether it's COVID-19 or gamma ray flash for astrophysics, or the Great Sumatra and Daman earthquake modeling for seismic modeling. So often all three of these problems are too large for a single group of scientists to handle, and they're too complex to tackle alone. So what we really need to do is to bring scientists from across the world to work collectively on these problems. Just to give you one specific example, this is the seismic hazard problem in the California and in the US. So a single problem like seismic hazard modeling often requires expertise from a number of different disciplines. So we have seismicity modeling, we have fault modeling, we have stress transfer modeling. So all of these are modeling different elements of the earthquake, whether it's deformation, for example, of the surface of the earth, movement, for example, of plates on the earth or parts of the earth, the velocity of travel, for example, of seismic waves. So all of these need to be put together in order to understand this single scientific phenomena, such as an earthquake. And increasingly, we also have availability of data which can help us understand this model better. So this is just an example of where scientists need to come together in order to be able to solve these large-scale problems. So if I come back to a more simple example of problem solving in general, particularly in the computer science area, this is just an example that suppose you have a child over here and the child's mother asks the child to go and pat the dog, for example. So the child will respond to this in a variety of different ways. So either the child will use a previous encounter. So if there has been a negative encounter with a dog in the past, the child will behave very differently. And also the child has an exploration instinct where they're trying to learn about new objects in their environment. So essentially the idea here is that the child is constantly learning about the environment, and based on a combination of previous experience and some inherent exploratory instinct. So what we can say, therefore, is that in some ways human beings are reasoning about the real world, and they're essentially very good model builders because our survival in the real world depends on it. So we have the real world here in green, which is often a very complex and fully difficult to fully understand. What we do as human beings in order to support our decision making and decision support, we try to build a model of the real world. And what we then do is we use this model and we refine this model with additional expertise or knowledge that we gain over time, using a combination of mathematics, logic, theories, and so on, and also our culture and our faith and our upbringing. So a combination of these two techniques helps us build this model in many ways. So if I look at the natural sciences today, like biology, chemistry, and physics, often these natural sciences observe the world and make hypotheses. They then test the hypothesis with data that they collect about the world, and they can use this as a way to confirm or deny the theory or the hypothesis they've made. So we only need one counterexample to disprove this theory. So the exploration of the world that already exists, so you're trying to observe the world as it exists at that point in time, and a natural scientist will explore the world that existed often when he or she was born. And discovery of a new phenomena is understanding of a phenomena that has already existed, for example, in the past, and relating phenomena in new ways that have not been previously understood. So that's really what natural sciences try to encourage or try to support as part of their working. So just examples are, Galaxy X was discovered in a part Y of the sky today. A new organism living in deep sea caves has been found and has been found to contribute towards the regulation of chemical Y. And chemical X and organism Y has been found to produce effect on the environment. So the discovery or finding new things are termed in these kinds of ways within the natural sciences. So Underpinning the natural sciences is scientific problem solving, which is common across the sciences. So what we try to do here is we state the problem, we form a hypothesis, and then we test the hypothesis through experiment design. We state the assumptions that we're making as part of this. And then the hypothesis is tested through data collection and analysis. And then from this data collection, we can draw conclusions in order to interpret the outcome. And we confirm limitations of these assumptions in some way. Another very important part of this scientific problem solving is the peer review process, where like similar scientists who might come from the similar types of domain, potentially those who have not worked with those individuals before are trying to validate independently either the outcome of the data collection or the data analysis process or the hypothesis that has been drawn from that data. So these are the different steps that underpin scientific problem solving. Engineering, on the other hand, which tries to extend the natural observation, that is, it leads to the creation of new phenomena, such as a new device or a new capability that has not been there before. So however, natural observations is also very key to engineering. It also employs the scientific thinking, as I mentioned on the previous slide, to confirm the hypothesis. So we're making the application of scientific observation and understanding as a way to extend natural observation, which often in some cases is taken as a given. So we admire our creative thinkers, right? And the question that often is asked is, what problem-solving capability do they have? And can we formalize this in some way? So do creative problem-solving require some magical gift, for example, that cannot be explained? And how do outstanding minds differ from ordinary minds in any special way? So one of the key things that we have learned over the past in scientific problem solving is that trying to bring a multidisciplinary team to solve a given scientific problem often leads to better solutions than a team that only comes from one discipline. So a multidisciplinary team approach is often essential in order to provide different perspectives onto the same problem. So in learning systems and in artificial intelligence, the idea is to build systems that learn from available good examples of a situation a system is likely to be in. And what we then try to do is to generalize for a new situation from what has been previously learned. So we do not directly program the system to solve a problem, but what we try to do is to give the system the capability to learn a solution itself based on things that it has already seen. Right? So essentially the system is trying to program itself, and then we validate the system on data or examples that it may not have seen as part of that learning process. So we're problem solving through learning from previous experiences. So for example, if I take these two problems, the distance from Beijing to Cardiff is 5,200 miles. If the average speed of an aircraft is 500 miles per hour, find the time it takes to travel from Beijing to Cardiff, right? So that's one problem. It's a numeric problem. And the second one is Bill's father's uncle is twice as old as Bill's father. 2 years from now, Bill's father will be 3 times as old as Bill. The sum of their ages is 92. Find Bill's age, right? So these are two kinds of problems. The question is, to what extent do computers really need to understand that the second problem refers to people and the first problem refers to cities that are in different parts of the world? So in computing, computer science is all about building abstractions, right? Something that differentiates it from other sciences and engineering. So for example, numbers, arrays, lists, right? These are all examples of abstractions. So data types, such as Bill's father, uncle, being represented as a string is a data type. We can have classes in Java, for example. We can have a vehicle class, for example, where a class inherits properties of something called vehicles. We can have mobile objects, etc. So each abstraction in computer science is a placeholder for something in the real world. And this abstraction primarily facilitates problem solving by removing unwanted information as part of the problem solving process. So the question is, right, that how we derive these abstractions then becomes critical. So the meaning of something, the semantics associated with something, lies in the way it connects to other things we know. So the more things you can connect something with, the more meaning it has. So this networked approach, this multiplicity of viewpoints, or the web of meaning, has also been explored previously in our arts in many ways. So for example, consider how a poet uses language, or the different meanings that you can have within a very simple joke, right? Where you try to make a twist on language, and consideration of analogies or similarities of views often gives both poems and jokes their meaning and context. So abstractions can be influenced by what we observe in the real world, both natural and physical systems around us. And a notion that we have derived from putting together different themes in our world will influence the specification of an abstraction. So how we encode and represent some abstractions is really critical, because the encoding is also a technique that helps us do problem solving. So how such abstractions interact with each other is also important. So this is a quotation from Marvin Minsky, who was a professor at AI at MIT in the US. So most expert adult thinking is basically much simpler than what happens in a child's ordinary play. It can be harder to be a novice than to be an expert. This is because sometimes what an expert needs to do can be quite simple. It's only hard to discover or learn in the first place. So how an expert represents such knowledge is therefore also critical to this kind of problem-solving approach. So in computer science, we're always trying to search for better ways to represent and abstract the real world. And abstraction should always allow us to be more creative in our problem-solving approaches. So the idea is to identify novel combinations of old ideas, maybe more suitable, for example, or easier to test or verify. So for example, consider a novelist who creates a parallel world to build a story, and then integrates these worlds to come together towards the end. So abstractions in some ways is creating these parallel ideas within a computer system as a way to represent the real world in different ways. Associated with an abstraction can be a range of concepts, and concepts can relate to the particular domain that we are interested in, whether it's music or molecules in chemistry, or an aircraft structure, for example, in engineering. So abstractions not only help us explore these conceptual spaces, but they can also help us to transform these conceptual spaces. So for example, a simple way to transform a conceptual space is to consider the negative of what we have. So for example, the person who discovered the structure of benzene in chemistry, Kekule, right? Before Kekule's discovery, everybody considered carbon atoms to occur in a straight chain, right? So where a ring was considered rather than a straight chain of carbon atoms, then the discovery of this type of new chemical was found. So creativity can therefore be a combination of old ideas, exploration of ideas within a given area, and the transformation of ideas within a given area. And the scientific thinking in computer science or building abstractions often allows us to explore these three things that you see at the bottom here. So computer science is about constructing more complex abstractions and then ways to manipulate these abstractions, whether it's in artificial intelligence and data processing or in computer games and avatars, and how we could utilize technology as a way to create artificial models of the real world to test these hypotheses. Right, so as our computers become more complex and become more powerful, our ability to handle more complex abstractions increases. So this is an example, for example, from Dolly Labs, where you can see here that this is all an artificially created world, as in a game. And each of the fish here is an independent being who not only interacts with the environment in which the fish occurs, but also has its own personality within this artificial game. Right, so this is an example of abstractions and the real world. So problem solving and creativity require building of useful abstractions and analogies, and computer science will facilitate both of these. So as computer and computational scientists, we need to build tools to support the scientific process and enable exploration of this conceptual space through the use of software as a kind of proxy for what a human would do, and provide support for collaboration between scientists to support multidisciplinary problem solving. And I will leave you with this, and I think this is why this competition is so important, because it brings together a combination of students across the world to look at interesting and difficult problems that we all face today. And I will leave you with this quotation from Africa. This is from Congo, a Congolese proverb, which says that a single bracelet does not jingle. So that means that if you work on your own, if you only have one bracelet, then that does not make any sound. It's multiple bracelets working together that creates impact and benefit for humanity. Thank you very much.